So now we are going to start the rheological characterization of magnetorheological polishing fluid. So now what are the components of MR polishing fluid? So it consists of CIP particles, abrasive particles and base media. So first what we do, we prepare the base media. So base media, it consists of paraffin oil and ep3 grease. So with certain composition, so initially we have started with 80% by weight of this paraffin oil and then 20% by weight this ep3 grease. We mix it and homogeneous mix it for a long time, for many hours, several hours, to make a homogeneous mixture. After that we mix these CIP particles, carbon iron particles, for a long time so that it can generate a homogeneous mixture. Okay. So now this MR fluid is prepared with a base media, paraffin oil base media. Now what we do, we mix abrasive particles there. So when we are then we start stirring it for a long time. So we have a stirring machine. So on the stirring machine it is rotated. This fluid is actually mixed for a longer time. Okay. So in a stirrer. So for several hours actually it is rotated. Then after mixing these abrasive particles, it will become magnetorheological polishing fluid. So these abrasive particles actually does not have any magnetic property. So only that CIP particles, it has a magnetic property. So this magnetorheological polishing fluid's magnetic property, it is different than this normal MR fluid, because these abrasive particles, it does not have a magnetic property. When these abrasive particles come into the in a line, when these abrasive particles comes along a chain path, so this chain structure actually breaks there. Okay. So we can see under microscope, so these chains, CIP particles chains, are not continuous chain. When abrasive particles comes here, so these chains breaks. Okay. So there is very few papers available in the literature who has taken consideration of this magnetorheological polishing fluid, because these abrasive particles, what happens, it will wear out the surfaces of the rheometer, so components of the rheometer. So that's why many people avoid that. So this experience can be conducted by taking proper precautions. So now this phase, different phase already we have discussed, this magnetic disperse phase, continuous base medium phase, and then these additives, and then we have added the abrasive particles there. Synthesis of MR polishing fluid already we have discussed. So this is MR polishing fluid, 20% by volume CS grade, 20% by volume silicon carbide with 1500 mesh size. And then common abrasive particles are silicon carbide, boron carbide, cerium oxide, diamond, alumina. So choice of abrasives are depends on the workpiece and workpiece material and hardness of this workpiece material. So base media is prepared by using ep3 grease and mineral oil. So we have used paraffin oil. You can use silicon oil also. Okay. So magnetorheological polishing fluid, here this schematically it is shown. When we are not applying any magnetic field here, these CIP particles and abrasive particles are randomly distributed here. Homogeneously it is randomly distributed. Now suppose you are applying some magnetic field, then immediately these CIP particles are forming chains. So these kind of long chains are actually forming. So outside these are the CIP particles and inside these abrasive particles. So abrasive particles are held in between these chains. So we are trying to show this schematically. This is not exactly the ideal case, but we are showing how it happens. Now when we are giving some shear force here at this direction, so these chains will try to rotate. So these chains are rotating. So when you are applying more shear rate, these chains will rotate more, and after some time what will happen, these chains will break here. These chains will break. When chains breaks, this MR fluid does not have certain time to recombine within these chains. Okay. So that's why this MR fluid, it has a shear thinning property. Okay. So when you are applying more shear rate, your viscosity actually reduces. With the application of high shear rate, this viscosity reduces. That's why this MR fluid has a shear thinning property. So now why we are doing this rheological experiment? Because this finishing efficiency and finishing quality of MR process relies mainly on the rheological properties of MR fluid, which must be characterized before using any specific applications. So because this rheological property means this finishing efficiency basically depends on the yield stress and viscosity of this MR polishing fluid. Because it is a non-Newtonian fluid, it is defined by the viscosity and yield stress of this fluid. Okay. So finishing efficiency basically depends on the rheological properties of the MR fluid. More yield stress of this fluid, it has a higher strength. Okay. So these properties are responsible for the bonding strength of these abrasive particles surrounding the CIP particles chains. So more the strength of this fluid will be more bonding strength to the abrasive particles, and these abrasive particles, more bonding strengths are there, then it will remove the surface angulations in a better way. MRP fluid composition and volume ratio have an impact on the rheological properties of the MR fluid. So these individual components of the fluid governs the rheological properties of the magnetorheological polishing fluid. So that's why it is required to predict what should be the concentration of CIP particles, what should be the concentration of these abrasive particles, what should be the concentration of this grease, what should be the concentration of your base media like paraffin oil. Okay, so that's why we need to find out what should the concentration of different elements of this MR fluid. So MR magnetological fluid, actually it is represented by three different models. All these are actually non-Newtonian model. So first one is the most popular, this is called Bingham plastic model. In the Bingham plastic model you can see tau equal to shear stress tau I plus eta into gamma dot. So tau I is the yield stress of this fluid, tau is the applied shear stress, eta is the plastic viscosity, and gamma dot is the shear rate. So in x-axis it is shear rate and in y-axis it is shear stress. So this one is the Bingham plastic fluid. So it has a certain yield stress. When applied shear stress is greater than this yield stress of this fluid, then only this fluid flows, otherwise this fluid does not flow. The second one is the Herschel-Bachler fluid, Casson fluid. Second one is the Casson fluid here. So this Casson fluid actually it is represented by root tau equal to root over tau c plus root over eta c and gamma dot. Here tau also same as applied shear stress and gamma dot is the shear rate. Tau c is the yield stress and eta c is the plastic viscosity here. Also MR fluid can be represented by the most popular, which is Herschel-Bachler fluid. Herschel-Bachler fluid can be represented as tau equal to tau I plus k into gamma dot to the power n. So these are the different fluids are there. So in Herschel-Bachler fluid, this N actually governs this consistency index. It governs whether it is shear thickening, whether it is shear thinning, or whether it is normal Bingham plastic fluid. So in Herschel-Bachler fluid, if you put this N equal to 1, then it will become the normal Bingham plastic fluid. When N is greater than 1, then it is shear thickening fluid, means its viscosity increases with the increase in the shear rate. And when N is less than 1, it is shear thinning fluid. So different rheometers are actually tried. Initially we have tried with capillary rheometer. So the advantage of using capillary rheometer is that it is very cheap to make, and it is easy to make also, and easy to use also. So here in our, and it has a certain similarity. It has a similarity in like our finishing process, MRFR finishing process. Like in MRFR process, this is the direction of the field, magnetic field, and we are flowing the deformation direction. We are flowing the fluid in the vertical direction, and in the horizontal direction we apply the magnetic field in case of MRFR process. So here you can see that these CRP chain structures are there. So these chains are forming horizontally. Now we are flowing this fluid along this vertical direction. Okay. So these are the reasons for developing the capillary magnetometer. Similarity with the MRP fluid flow in MRFM. Presence of abrasives in polishing fluid damage the surface of the commercial available rheometer. High yield stress of MRP fluid in magnetic field, and then simple in construction, this capillary rheometer. So you can see this first design of that capillary rheometer. So this is the container here. So constant temperature jacket is actually it is kept here, so that this temperature of this MR fluid can be maintained in this jacket, in this container. This temperature can be maintained here. So it is filled up with the MR polishing fluid here. Okay. So this is the capillary tube. It is attached just at the bottom of this container. Okay. Now we can see this is the core material of this magnet. It has to be maintain certain ratio. L by T ratio should be more than 0.4. So here diameter of this tube, it is 2 millimeter here. Internal diameter of this tube is capillary tube is 2 millimeter. Okay. So length of this two flat actually plates are actually fixed just outside this capillary tube. So the length of this capillary flat plate is 60 millimeter. Okay. So there is a container is there to collect the MR fluid which is coming outside this, coming through the capillary tube. After steady state is reached. Obviously it is after steady state is reached. So this MR fluid is flown by using a compressor. So there is a compressor entry here. So through this compressor is coming. So there is a gauge is there, pressure gauge, digital pressure gauge. From this pressure gauge actually you can measure whatever the pressures are there inside that container, MR fluid container. Okay. So this is the electromagnet here. This is the core material of this electromagnet. In front of the core material, two flat plates are actually fixed, and this is the capillary here, and this is the container to collect the MR fluid just below the capillary. So this can sustain up to pressure of 7 bar, because when we have started doing experiment using this rheometer, what we have seen that because of we are using compressor, so it is making a hollow channel inside this MR fluid. Okay, so it is very it is very difficult to maintain a uniform pressure just above the MR fluid layer. Okay, so it is very difficult to maintain a uniform pressure inside the container. So that's why this design is discarded, and then we have developed one more design. So we shall show here. So it is we have used our similar setup of MRFF setup for measuring the viscosity of this polishing fluid. We have used the similar setup for measuring the viscosity of this polishing fluid. Here what we have done, this is the capillary here. Just outside this capillary, we kept this magnet, electromagnet here, and this MR fluid actually it is flown by this hydraulic unit. So this is the piston here, MR fluid piston. So it is MR fluid is flown through this hydraulic unit. Okay, so this is the top media cylinder. So initially this top media cylinder is filled up with MR fluid. After that, this total attachment is attached. This total attachment is attached to this top media cylinder. Okay, just below that, we have fixed our this capillary tube, and just outside this capillary tube, we kept these two plates for applying this magnetic field. Okay, so in this configuration, so advantage is that we can measure the viscosity of this polishing media in the same setup, and here our magnetic field, direction of this magnetic field, this is the direction of this magnetic field, and MR fluid is flowing in this vertical direction. So you have to measure the viscosity of this fluid so that this fluid deformation shear direction and also this magnetic field direction should be perpendicular to each other. So this is the container here. Here you can collect the MR fluid. After this MR fluid, inside this capillary has come to a steady state condition, and you have to collect the MR fluid after that steady state condition inside this container here, and you have to measure the time. So from this time and from the weight and from the density of this MR fluid, if you know the density of this MR fluid, okay, so you can calculate the volumetric flow rate of this MR fluid, that is Q, volumetric flow rate of MR fluid. So that is millimeter cube per second. So this is the volumetric flow rate of MR fluid, you can calculate. So only thing you have to calculate here, volumetric flow rate. And at the same time, we know the pressure, how much pressure we have given from the hydraulic unit. So we know the pressure difference, pressure gradient across the capillary, and we know the volumetric flow rate. And if we know these two parameters, we can calculate the yield stress and viscosity of this fluid using this capillary diameter. So this container, it contains 130 centimeter cube. So here this MR fluid container, it contains 130 centimeter cube of cubic centimeter of fluid. So this is the experimental setup. Same experimental setup of MRFF process is used for capillary diameter. Here you can see this is the magnets, C-type magnets are used. So this is the magnet, and this is the core material here. In front of that core material, you can see two plates are actually kept, and this is the capillary here, and into this portion, at this portion only, you have, so at this portion only, this magnetic field is applied using these two flat plates which is attached to the core material. So we can collect the polishing media here just below this capillary for a certain time after it is reached to the steady state condition. So this is the calculations. So this is the cylindrical capillary, it is shown. S is the shear stress here. So this is the length, L is the length of this capillary. So in our case, L is the length over which magnetic field, we are applying the magnetic field. 2R is the diameter of this capillary. In our case, we have considered 2 millimeter diameter of this capillary tube through which we have flown the MR fluid. And shear stress at the wall, we have calculated as, it can be calculated as del PR by 2L. Del P is the pressure gradient, so how much pressure we are giving across the capillary, so that we know from the hydraulic unit how much pressure we are giving. R is the radius of the capillary, L is the length of the capillary over which we are applying the magnetic field. And final equation for the viscosity calculation is 4Q by pi R cube. Q is the volumetric flow rate of this MR fluid after steady state is reached, which we have measured during experiment. R is the radius of this capillary. Eta PL is the plastic viscosity. SW is the shear stress at the wall of the capillary. And psi is the yield stress of this fluid. Okay, so this is the equation. So y-axis is rate of shear 4Q by pi R cube, and x-axis it is the shear stress at the wall. So at different pressure, by changing the pressure, we can get different rate of shear. So Q already we know here, volumetric flow rate, at different pressure we can calculate. And at different pressure we can calculate what is the shear stress and what is the rate of shear 4Q by pi R cube. So by plotting these two, for rate of shear and shear stress, at different pressure we will get this line. So this line, when it is, you have to do a curve fitting using a line, using a straight line. And at this point, you have to just extrapolate to this x-axis. Why? Where it is extrapolated, where it is touching to the x-axis, that point will give the 4 by 3 psi. Okay. And so that value of shear stress divided by 4 by 3 will give the yield stress of this fluid. Okay. And the slope of this curve will give the 1 by slope of this curve will give the plastic viscosity. Okay. So this 1 by slope of this curve, slope equal to 1 by eta PL, which will give the plastic viscosity. Okay. So, this capillary viscoreometer is a very important instrument for measuring the viscosity of this MR fluid on the same MRFF setup. So after that we have started working on parallel plate rheometer. So Anton for NCR 301 rheometer is used. They have a magnetorheological device there to apply the magnetic field perpendicular to the flow direction. So this is the bottom plate here. They have two parallel plates. So this is the bottom plate, which is sandblasted in our case, and there is a container kind of thing. So protrusion is kept there. Okay, so here actually we have to keep our MR fluid so that, so this diameter of this bottom plate is 20 millimeter, and this is the top plate here. This is the top plate. It should be kept vertically by reversing the direction, reversing its direction. So it is called tool master. So this top surface of this tool master is sandblasted. So this is the parallel plate, this is top plate here, this is the top plate, and this is the bottom plate here. So we are applying magnetic field just perpendicular to these parallel plates. Now we are rotating this top plate here with a certain RPM. So this RPM is proportional to the shear rate of this fluid. And when you are applying when you have applied some magnetic field, and now we are trying to rotate this top plate, tool master, it will generate a reverse torque. So this reverse torque is actually proportional to the shear stress of this fluid. So shear stress of this fluid is proportional to the torque, and shear rate is proportional to the RPM of this top plate. So at different rotation, at different shear rate, you will get different shear stress, and these values you can plot. Okay. So this is the shear rate and shear stress. At different shear rate, you can plot the shear stresses, and these values you can connect or you can fit using three different equations which are used for modeling of magnetorheological fluid. So this Bingham plastic, Herschel Wagner and Casson fluid. So we have fitted these three equations, fitted these points using these three equations. Okay. So after fitting, so we calculated the R square value for all the three equations. So for Herschel Wagner, Bingham plastic and Casson fluid model. So total 30 experiments are carried out using CIP concentration of minus 15, concentration of 15% to 35%. So we have varied CIP particles, carbon nanoparticle concentration from 15 to 35%, abrasive 7.5 to 17.5%, grease 6 to 14%, and magnetic field from 0.2 to 0.6 Tesla magnetic field. So these are the four variables are there, and we have varied, and experiments are carried out using center composite rotatable design. And what we have measured here, we have measured yield stress and viscosity of this fluid. So after fitting these things, so from this is the Bingham plastic, this is the Herschel Wagner, and this is the Casson fluid. So you can see there, so this is the yield stress from the Bingham plastic model, and this is the plastic viscosity from Bingham plastic model. So from Herschel Wagner model also you can calculate the yield stress and viscosity. From Casson fluid also you can calculate yield stress and viscosity after fitting all these points. So we have checked the yield stress and viscosity. So what we found that R square value from all these 30 experiments, we have seen that R square value is maximum for in case of R square is the nothing but is the fitting parameter, for car fitting parameter. So its value is near to 1 means it is high, very good fitting. 0 means it is very poor fitting. So in case of Herschel Wagner model, we can see this R square value is very high in case of Herschel Wagner model. So Herschel Wagner fluid actually it fits to the data points obtained from the rheometer. Okay. So for that, what we have done, yield stress is calculated from the Herschel Wagner model, and viscosity, post-yield viscosity is calculated from the Bingham plastic model. After that, we have done the ANOVA study, and what we have seen that for yield stress, magnetic field has the highest contribution for the yield stress, then CIP particles has the next contribution, and abrasive and grease they have a very less contribution. So magnetic field has a 57.65% contribution, and carbon nanoparticles has a 10.71% contribution on yield stress of this fluid. Then we have done the optimization study, and we have found that so this 30% CIP, 10% abrasive particle, and 12% grease will give the, and at 0.5 Tesla magnetic field will give the highest combination, which will give the highest yield stress of this fluid. And this is the regression equation to calculate the yield stress. And similarly, ANOVA is done for the viscosity model also. So what we have found that here also this magnetic field has very high contribution, 53.62%, 17.68%, but abrasive and grease they don't have that much contribution. Okay, so these are regression equation for the viscosity model. Now we have to do the, after doing this rheological study, we have to do the magnetic characterization also. This magnetic characterization of MRP fluid is carried out in vibrating sample magnetometer. It is called VSM. So there magnetic field is varied from minus 1.75 Tesla to 1.75 Tesla, then it will come back to again minus 1.75 Tesla. And MR fluid is kept inside a container, small container, and it is gone through a huge magnetic field minus 1.75 to 1.75. So now here you can see this one in this zone, it is exerted here. You can see these two lines, one is for forward and another one is the backward. Okay, so this hysteresis loop you can see, it has a very less remnant magnetization. Here you can see this remnant magnetization is very less. So this is the main property of the CIP particles here. So it has a very less remnant magnetization, means when you are removing this magnetic field, immediately whatever the CIP particles are there, because it does not have any remnant magnetization, it will not agglomerate. So it will immediately it will be demagnetized. Okay, so there is a less chance of agglomeration in case of this MR fluid which is prepared using CIP particles. So it has a pore excipibility of 13.7, saturation magnetization of 141 EMU per gram. Saturation magnetic flux density here it is 1.6 Tesla, and of all the experimental results whatever we have shown earlier, lowest saturation magnetization we have found 1.098. Okay, so lowest saturation magnetization which is found 1.098, and we have applied the magnetic field as 0.6 Tesla. So our rheological experiments are not affected by the magnetic saturation of the MRP fluid. So effect of CIP and magnetic field, effect of CIP concentration and magnetic field. Here left hand side it is yield stress and right hand side it is viscosity. You can see with the increase in the magnetic field, your yield stress actually increases. With the increase in the magnetic field, both yield stress and viscosity actually increases. So if you are applying more magnetic fields, these more strong CIP chain structures are forming. So the CIP chains will form from single columnar structure to a single structure to columnar structure. So it will become a very thick structure. So these abrasive particles will be held with a very higher force there. So more bonding strength will be there, more dipole moment will be there. So that's why you will get higher yield stress and viscosity of this polyester media. So this is the force acting on a single CIP particle can be calculated as M chi m B del B by mu 0. M is the mass of this spherical abrasive particle, chi m is the mass susceptibility of this CIP particle, B is the magnetic field intensity, del B is the gradient of this magnetic field intensity, mu 0 is the permeability in free space. So all these experiments are shown here, 30% CIP, 10% abrasive and 12% grease and 0.5 Tesla magnetic field. So with the increase in the magnetic field on CIP concentration, you can see both yield stress and viscosity increases. Why with the increase in CIP? CIP concentration increases means more thick structure increases. Structure of this CIP chains also increases with the increase in the CIP concentration. Okay, so it will become more strong. And when you are applying these abrasive particles, you can see from 20% CIP, so this is almost yield stress almost constant, but at 25% to 35%, you can see here this yield stress actually reduces. Similar thing actually happens for this one viscosity also. So that's why if we increase more abrasive particles there, what happens? These abrasive particles being a non-magnetic in nature, it does not have any magnetic property. So it will, when it comes in between this chain structure, this if some chains are actually continuous chain, it will break into two pieces. Okay, so this chain strength actually reduces. So that's why with the increase in the abrasive particle concentration, this viscosity and yield stress actually reduces. And also with the increase in the grease concentration also, we can see that this yield stress and viscosity of this fluid also reduces, because grease actually acts as an inhibitor. For a certain fixed magnetic field, if we increase the grease, it will resist the CIP particles to come in a chain. Okay, so with the increase in the grease, our yield stress and viscosity of this polyester fluid also reduces. So from this figure, we can see here that with the increase in the shear rate of this fluid, this viscosity of this polyester fluid, it is reduces drastically. So from this figure, we can say that this MR fluid is a shear thinning fluid. So here also we can see with the increase in the shear rate of this fluid, shear stress of the fluid also reduces here. So this gradient actually reduces. You can say this gradient actually reduces. So from this shear stress profile also we can say that this MR polyester fluid is a shear thinning fluid. So from this schematic diagram already I have discussed this one. When we are increasing more shear, this CIP chain structure actually breaks, and it has little time to recombine. So MR fluid actually behaves as a shear thinning fluid. So now we shall discuss the experimental results on flat workpieces. Rotational MRFF experimental results on flat workpieces. So we have considered flat workpieces. Now we have considered three different kinds of workpiece. One is brass, stainless steel, and then ENet workpiece. So this is the effect of rotational speed of this magnet. So now we can see that with the increasing the rotational speed of this magnet, your change in RA means initial RA minus final RA increases, and it reaches to a certain value for both three different materials. So at what point it reaches, it gives the optimum RPM of the magnet. So this is the optimum RPM of the magnet where change in RA is maximum. After that you can see that surface change in RA actually reduces. With the increasing the rotational speed of the magnet, what happens? Your centrifugal force increases. So indentation into the workpiece surface increases. Also your tangential cutting force also increases. And if we are increasing with the RS means with higher RPM, so these abrasive particles, it covers with the more area into the workpiece surface, more area of the workpiece surface. So that's why your change in RA actually increases with the increase in the RPM of the magnet. But beyond that optimum RPM of this magnet, what happens? This change in RA again reduces because we have discussed that shear thinning nature of this MR fluid. So at high shear rate, you are increasing RPM means you are increasing shear rate. With high shear rate, this MR fluid would not able to sustain the structure. So this chain structure actually breaks. So that's why with the increasing the rotational speed of this magnet, your shear means surface roughness also reduces. Now here you can see this is the change in material ring wall. With the increasing the rotational speed of this magnet, material ring wall increases. Here you can see at high RPM, this material ring wall also increases because at high RPM, because of this random penetration of these abrasive particles into the workpiece surface, so material ring wall increases, but their surface finish actually deteriorates. Now we shall discuss one more thing is that ENet is the magnetic material, but stainless steel we have considered as non-magnetic here. We have used non-magnetic stainless steel. Brass non-magnetic, it is also non-magnetic. We have seen that for magnetic ENet workpiece, we got very less improvement in surface finish. Why it is so? So you can see this magnetic field vector plot here for stainless steel workpiece and for ENet workpiece. So these are the ENet workpiece here. When you are applying some magnetic field, what happens? There is a local magnetization takes place in between this magnetic pole and the workpiece. Okay. So because of this local magnetization, the strength of this magnetic field inside this MR fluid actually reduces. And individual workpiece actually this workpiece it becomes a magnetic material. And what happens? Whatever MR fluid is there, it sticks into these magnetic workpieces. For polishing actually we need a relative motion. As MR fluid actually sticks into the workpiece surface, there is no relative motion in between this workpiece and this MR fluid because there is a certain layer of this MR fluid actually which sticks to the workpiece surface. So that's why it sticks. Now that's why there is a less relative motion is there in between this MR fluid and the workpiece. So there is a very less improvement in surface finish. Also you can see from this figure, these magnetic contour lines, here it is totally uniform, but here these magnetic contour lines, it is not uniform. It is concentrated towards the magnetic workpiece. So that's why with magnetic workpiece we got very less improvement in surface finish. So this is the ANOVA we have done with 4 parameters: hydraulic extrusion pressure, finishing cycles, rotational speed of the magnet, and volume ratio of CIP and SiC. CIP and silicon carbide abrasive particles. We have considered 0.34 to 4. Hydraulic pressure we have considered 32.5 bar to 42.5 bar. Finishing cycles we have considered 400 to 800, and rotational speed of the magnet we have considered 20 to 100. So by considering all these things, we have found that rotational speed of the magnet has highest contribution, finishing cycles also has contribution, and pressure also has highest contribution. Okay, and A square also has a contribution, 18.47%. So these are the significant parameters: pressure, cycle, and rotational speed of the magnet. Although CIP by SiC, ratio of the CIP by SiC also significant, but his contribution is less. Okay, so that's why it is not that significant a parameter in this case. So these are the 2 workpieces we have considered. One is stainless steel, another one is the brass. So this is the optimized parameter: 39 bar pressure, finishing cycle 660, 67 RPM, and CIP by SiC ratio of R. And we got 45.27% improvement in surface finish. So here also you can see with the increasing pressure, surface finish improves. Percentage reduction in RA it is calculated as initial RA minus final RA by initial RA multiplied by 100. It will give the percentage reduction in RA. With the increasing pressure, percentage del R increases and it reaches to an optimum value. After that, actually it stalls. With the finishing cycle also, you can see initially there is a high improvement in surface finish, but after some time you will see when this finishing cycle increases, it stalls after some time. Okay. So with the volume ratio of CIP by SIC, you can see there is an optimum value. Up to this optimum value, if we increase the CIP by SIC ratio, the surface finish improves. After that it reduces, because up to certain value your CIP percentage increases. As the CIP percentage increases, more strong bond actually will form. Abrasive particles will get more strength to the polishing, for polishing. But when the CIP percentage is increasing more, beyond a certain limit, abrasive particles will be less. So in that case, less abrasive particle, it is because of this less abrasive particle, it is very difficult to do the machining, polishing. So because without these abrasive particles, there will not be any polishing to happen. So these are rotational speed of the magnet. Its effect on percentage del RA. It increases with the rotational speed of the magnet. Surface finish improves. After that, due to the shear thinning nature of the fluid, it stalls up, reduces after some time. So this is the SEM picture using Magnetorheological abrasive for finishing. So this is the grinding lay direction. Grinded workpiece, initial workpieces are grinded. So this is the grinding lay here along this direction. So you can see here these perpendicular marks are there. So which is MRFF lay, which is perpendicular to the grinding lay. So after MRFF, you can see lots of peaks and valleys are available here. But you can see with RMRFF process, you can see these valleys are actually separated by long distance. So these valleys are actually separated by long distance. Okay. So this kind of process patterns also you can see it is generated on the workpiece surface. So this is the brass workpiece. This is the grinding lay for this brass workpiece. Here definitely in MRFF process itself we got a very good surface finish. But these kind of scratch marks are there. So valleys are there, but using this RMRFF process, rotational MRFF process, you will see these process patterns and all these valleys are completely removed. So this is the FM image for stainless steel. You can see these kind of undulations are there because it is grinding operation. Okay, so using MRFF process without rotation, these valleys you can see it is clearly visible. But using RMF process, you can see these valleys are almost removed. Although few deep grinding marks are there, it is not removed. By using this MRFF at optimum rotational speed, you will see all these values are totally removed. Similar case for this brass also, you can see these undulation, surface undulations are there. So these deep grinding marks are there in MRFF process without rotation. So with rotation, you can see we got this 0.09 at 20 RPM and 0.05, 50 micron we got at 67 RPM. So these are the initial ground surface for stainless steel and brass. So now it is reflected, you can see at the after finishing, this IT component is reflected for steel and for brass also. So these are the surface roughness profile, initial surface roughness profile, final surface roughness profile. So this final surface roughness profile, you can see it is almost flat in case of MRFF or MRFF process, stainless steel, for stainless steel. For brass workpiece, you can see it has become totally flat. For brass workpiece, this surface roughness profile, it becomes totally flat. So we got 50 nanometer in case of brass workpiece and 110 nanometer in case of stainless steel workpiece, final surface roughness value. So this is the bearing ratio curve. So this is the initial bearing ratio, this is the final bearing ratio. At 60 RPM, we can see, so this bearing curve actually becomes flats after polishing. But for brass workpiece, you can see this bearing ratio curve, it becomes almost flat, totally flat. So higher the flatness of this bearing ratio curve, you will get more contact area. Okay. So you can see this bearing area curve also improves using this MRFF process. So after that, we have done the experiments on cylindrical workpiece. So we have used this rotational Magnetorheological abrasive finishing process for polishing cylindrical internal surface of cylindrical workpieces. So this kind of cylindrical workpieces we have used. So after MRFF, we have checked the surface roughness at different places, and after RMRFF, we have checked the surface roughness at different places. We have seen that almost uniform polishing we achieve by using this rotational MRFF process. So here also we have checked effect of rotational speed of the magnet on percentage change in RA. Also we have considered del outer roughness. So outer roughness, because our workpiece is cylindrical workpiece. As we have considered cylindrical workpiece, so in naked eye you will not see any undulations, but in outer roughness measuring machine, if you see, so this kind of two circles are there. So this kind of profiles will get. So here this is the circumscribed circle, and this is the inscribed circle. Okay. So this distance between the circumscribed circle and inscribed circle will give the outer roughness. So this is the mean surface roughness profile here. So this outer roughness is very much important when these when some rotating parts are there. Okay, it should be perfectly circular. Its cross section should be perfectly circular. So we have seen that RMRP process is capable of improving the outer roughness of the cylindrical workpiece. So this is the surface roughness profile. We see that at 150 rpm we got the very good surface roughness, and here also 150 rpm we got the very good outer roughness. Also we can see here metal removal also improves with the increase in the rotational speed of the magnet. So at optimum shear rate, what happens? These surface peaks are easily removed, and when we are shear rate or RPM, with the increase in the RPM, shear rate of the fluid also increases. When your shear rate of the fluid is beyond the optimum shear rate at that time, because this fluid is actually, this chain structure are deformed. Okay, so this chains actually, it has less force in between the CRP particles. So instead of cutting a certain height, it will rotate and adjust the height of the peak height, or it will adjust, these abrasive particles will adjust the depth of cut, and it will reduce the small peaks from the workpiece surface. So with the increase in the rotational speed of the magnet, your surface roughness deteriorates beyond the optimum surface, beyond the optimum RPM, surface roughness deteriorates, and also its outer roughness also deteriorates, although its metal removal increases. So with mesh size also we have seen, we have considered the silicon carbide abrasive particles. With the increasing the mesh size means we are reducing the size of the abrasive particles. So suppose from right hand side to left hand side, if we consider from smaller size abrasive particles, we are considering to the bigger size abrasive particles here. With the bigger size abrasive particles, it will remove the surface undulations with a bigger cut. Okay, so surface roughness improvement reaches to an optimum value, and beyond that, actually what happens, these CRP particles, because this abrasive particle size is too high, then the smaller size abrasive particles, CRP particles is not able to give the bonding strength to the bigger size abrasive particles. The normal trend is that you have to use similar size of abrasive particles, and so you have to use similar size of abrasive and similar size of CRP particles. Also with the bigger size abrasive particles, these kind of scratch marks are also generated. So because of the scratch marks on the already polished surface, we got a lesser improvement in surface finish beyond this optimum value, optimum size of the abrasive particles. So with finishing cycle, we can see surface finish improves. Here at 1600 finishing cycle, very good surface finish is observed. But beyond this 2400 finishing cycle, we can see this kind of hazy surface is obtained, because at that time these abrasive particles actually give scratch marks on the already polished surface. Here you can see this without finished surface is achieved. Here, because these abrasive particles are actually giving the scratch marks, putting the scratch marks on the already polished surface. So beyond this optimum finishing cycle, okay, so your surface finish deteriorates. So these kind of scratch marks are generated. So surface this outer roughness also improves with the finishing cycle. So we can see here from 7.072 we got this 4.81 means outer roughness. So again we have done the experiments, design of experiments using hydraulic extrusion pressure of 32.5 to 42.5 bar, finishing cycle of 600 to 1400, rotational speed of the magnet from 50 to 250, and mesh size of the abrasive is 90 to 210. So here we can see that rotational speed of the magnet has given, we got the highest contribution, then finishing cycle, then finishing pressure. Then again A square also, square of this finishing cycle, rotational speed of the magnet also gives higher contribution, so it is also a very significant parameter. For outer roughness also, we got this finishing cycle is the important parameter, significant parameter, most significant, and then this is the pressure, and also some cross parameters are there, N into An and A square also there. So this is the optimum process parameter, 40 bar pressure, finishing cycle 1200, magnet RPM 149, silicon carbide mesh size are 153, we got 94.14% improvement in surface finish. So this is the integration equation for this percentage change in RA, and for change in outer roughness, this is the regression equation. So after that we have done the parametric study. With the extrusion pressure you can see percentage in RA increases, after that it stalls. Changing outer roughness also with the RPM it increases because of higher centrifugal force, higher tangential cutting force. After that, due to the shear thinning nature of this fluid, it stalls. So this shear thinning nature, it is shown here. Rotational speed, we affected rotational speed on percent change in RA again. You can see when you are increasing the rotational speed of the magnet, after some time it will happen that helical path of the abrasives and genetics marks. Okay, so whatever this workpieces, actually it is made by boring operation. Okay, the stainless steel workpieces are made by boring operation into the boring operation. When we are using this, when we are increasing this RPM of this magnet, after some time you will see this, whatever genetics marks are there, and this helical path of the surface particle they takes and the similar path. So instead of cutting, it is following the same grooves, so that's why it is not cutting. But with the increase in the rotational speed of the magnet, you can see here, your arc length actually increases. So it is taking more path, considering it is covering more path on the workpiece surface. That's why your surface roughness improves initially, but after that, because of this, it is taking the same path. So that's why surface roughness deteriorates. With the mesh size also, you can see with the already we have discussed, with the increase in the mesh size, your smaller size abrasive particles are there. So more abrasive particles are taking part in the polishing. So that's why surface roughness improves. After that, if we increase the mesh size of the abrasive particles, more abrasive particles will be there. Okay, so there will be less CIP particles to give the bonding strength to the fluid. So with the increase in the finishing cycle also, you can see percent change in RA increases. Initially there will be a high rate of change in RA, but later it stalls. Initially this loosely held material actually it is removed. After that, proper peaks and valleys are actually available. So these abrasive particles takes actually initially these peaks are actually very high, so it is very easy to cut. But after that, this width of this peak actually increases. So that's why after some time it is becoming difficult by the abrasive particles to cut the surface peaks. So this is the initial workpiece surface. This is the final workpiece surface. You can see after polishing this kind of mirror finish surface we achieve. So this is the initial workpiece surface. This kind of surface undulations are there. So these are the genetics marks are there. And after polishing, you can see this kind of cross-hatch patterns are actually generated. So this kind of cross-hatch patterns are required for this cross-hatch patterns are required for cylinder boring operation. For in piston cylinder, that inside cylinder it is actually honed surface are there. So this kind of cross-hatch patterns are generated. It helps in oil retention. So initially this kind of undulations are there because it is boring operation. So that's why this kind of genetics are formed. After that, you can see this kind of flat surface is generated, almost flat surface we achieve. Very high surface finish as 16 nanometer. So this is the same image. Initial workpiece surface, RMFF with 150 and rotational MRFF process at 250 RPM. With optimum RPM, we can see very good surface finish is achieved. But at high RPM, the surface particles, because of this, they are random marks. The surface finish actually deteriorates. So initial surface outer roughness we got after boring operation it is 5.17 micron, and after polishing we got 3.39 micron final surface finish.